Good morning, everyone. I'm sorry I'm not being in the conference to give the presentation face-to-face, so I take this video and ask the professor to play it for me. So if you have any question, please don't hesitate to send the email to my address and to the address of our professor. Okay, let's begin. The title of my presentation is the event-driven boundary control for time fractional diffusion system on the time varying input disturbance. My presentation will be divided into the following 5 parts. The first part, I will give some motivations of our study, and then we state our problem. And in the third part, we are focused on the event-driven controller design and implementation. And I will give a numerical example, and then the summary and extended. For the motivation of our paper, I will try to answer the following 2 questions and give some applications. For the first question, why fractional? I will first give some subdiffusion processes in our real world. The subdiffusions I usually describe those phenomena which get trapped by local imperfections and then released due to the thermal fluctuations. For example, the swarm of robots moving through forest, or the proteins diffuse across a cell membranes, or the flow through porous media. For those subdiffusion processes, the MSD, which is the sort of the mean squared displacement, is not a linear function of the time t, like the normal diffusion process. The subdiffusion process, the MSD of the subdiffusion process is a power law function. Is the power law function. The order of its MSD is less than 1. For example, when alpha is equal to 0.5, it looks like this, which diffuses slower than the Brown motion. And other part, which is called the super diffusion, and the MSD, the order of its MSD is bigger than 1. For example, when alpha is equal to 1.5, it looks like this, which diffuses quicker than the Brown motion. From those 3 references, one is in 2000 and other is a new one is in this year. And from this picture, we can see that the date made from this subdiffusion satisfy a power law function. Look like this is a power law function P. However, to introduce why we use the fractional order system, we introduce a function which is called the Mittag-Leffler function, which can be regarded as an interior of the exponential function. Here you can see his definition. When alpha is equal to 1, is the exponential function. For the Mittag-Leffler function, from this reference, we can get that it is constrained by 2 power law functions. For example, when alpha is equal to 0.35, it looks like this. The red line is the Mittag-Leffler function, and the blue one and the black one are these 2 power law functions. And the same with the same to alpha equal to 0.75. Moreover, we claim that the solution of the fractional order systems are usually expressed by the Mittag-Leffler function, so its stability should be called Mittag-Leffler stability, and also called power law decay. This is different to the interior order, which is usually called the expressional stability. Okay, let's look at this picture. For those phenomena in the complex system, which has characters such as the scale theory, heavy tardiness, long range dependence, and long memory, we can use the fractional order dynamic to model them, which can be shown power law, Mittag-Leffler law, which is also called power law. For more knowledge on those processes, we refer the readers to read this book, which is written by the Bruce West in 2016. Okay, next I will try to answer the second question. Why event-driven control? In many control applications, controllers are nowadays implemented using digital communication networks, in which the control task has to serve the communication resources. As a consequence, if we use the time-triggered fashion, where the control tasks are updated periodically, however, this design would lead to overutilization of the available communication resources or causes a limited lifetime of the battery-powered device. To improve this, here we try to introduce another control style, which is called the event-driven control, where the control action is done only when the desired driver event is breached. For example, we look at this picture. The left one is the time-triggered control style, and the right one is the event-driven control scheme. From this picture, you will see that the number of the updater is smaller than that one for event-driven control scheme. Okay, in this paper, we will try to study this system, where the first part is called called the Capotal fractional derivative, and this is the Laplace operator, and the sigma here is a continuously differentiable function, which is right at C1, and this part is the boundary condition of the system, and the left boundary is 0, and the right one is here U denotes the control input, and D denotes the time varying boundary input disturbance, and this part is the initial condition. Okay, next we will try to design some more filter to estimate the input disturbance. Okay, from the book in 2000, written by Harry, the author claimed that time fractional diffusion system is usually used to model the transport process, especially in homogeneous environment. Typical examples include the chemical reaction processes in dispersive transport media, or reheating process of the heterogeneous metal slabs. So, here this is called the system 1. The system 1 can be regarded as a model of thin space in homogeneous road with state y-axis and the boundary impulse acting on the right side at equal to 1. Okay, before stating our main results, we give some basic results on the fractional calculus. This part is called fractional integral, which is given by Riemann-Rolle, and this is the Capotal fractional derivative when alpha equal to 1 is the usually partial which is usually the partial derivative on time t, and this is the case when alpha belongs to 0 to 1, provided that the right side is pointwise defined on 0 to infinity. Okay, when the control inputs are updated in event-driven cases, the system 1 can be rewritten as this one is called the system 2. Similar to our program once work in 2016, the integral transform could transform the system 2 into this target system. You can see from this target system, we can prove that this target system is metagonal lifeless stable. Then we should show that the kernel of the integral transform exists, so we can prove that the system 2 is also metagonal lifeless stable. Okay, from this transformation, we can show that the kernel should be granted by the following hyperbolic PDE. And from the results in this book, the following results hold. And if sigma is a continuously differential function, the system 5 has a uniquely bounded solution. And moreover, if we define the integral transform as the operator G, we can prove that both G and its inverse are bounded. So with this, we can obtain that this integral transform exists and bounded, and its inverse also bounded. Then we can say that those two systems are equal. So if this system is metagonal lifeless stable, then this also metagonal lifeless stable. Okay, for the boundary for the input disturbance, we design a low pass filter as follows, where the function f should satisfy this condition, which is a low pass filter in the frequency domain. Design the event driven boundary controller as follows. Look like this, where d hat is the estimator of the disturbance. Okay, if all components of the state vector for the considered system can be made by network sensors, assume that the first event happened at t0, at t0 equal to 0. We then design the next instant tk plus 1 is equal to like this. Then we obtain our first main results. Suppose that the 8 here is the 8. The condition on the estimator of the disturbance holds, and all conditions of label 1 are satisfied. Then if d omega and are bounded and their Laplacian transform exists, then the closed loop system 1 under the event driven rule 10, this is asymptotically stable. For the cases of the time, we omit the detailed proof. Okay. Next, for the event-driven control style, there exists a case where an infinite number of transmissions in a finite time, to avoid this, which is called the Zimmer phenomenon. To avoid the Zimmer phenomenon, a positive loner bounded inter-event time should be granted. So then we obtain our second main results. Suppose that our condition of variable first hold, then the minimum inter-event time t minus given like this between two time should be loner bounded, provided that tk is defined as the equation 10. Okay, we omitted the detailed proof too. Okay, to illustrate the effectiveness of our main results, we consider a numerical example where alpha is equal to 0.5 and sigma is equal to 15. This is the boundary condition, and this is the initial condition. Let lambda equal to 1 in the system 4. The solution of the hyperbolic PDE of the kernel of the integral transform should be given like this, where I1 represents the modified Basel function of order first. To test our event-driven control methods, let dt, the disturbance of the input, is equal to a same function, and the event threshold constant in the event-driven condition is very small, is 0.005. So with those parameters, we can give the numerical like this. When u is equal to 0, this is called the open up. The solution is look like this. Of course, it obviously is unstable. And for the closed loop system, when the UT is designed as the event drive control, the plot of YT is look like this. It's asymptotically stable. And this picture is show the event driver instance. It's look like this. This is the event driver time instance. Okay, finally, we'll give our summary and experience. In this paper, the idea of using state, this is the state feedback event drive control to asymptotically stabilize anomalous subdiffusion processes governed by time fractional diffusion system with unknown time varying input disturbance is presented. To address this problem, a UDE-based estimator is proposed to evaluate the disturbance. The main stability results are obtained by using the backstabbing technique, which is on a state feedback event drive controls. However, in many practical cases, the available for state measurement may be impossible due to the difficulties in measuring. To solve this limitation, we will try to use some methods. For example, we try to design a sensor for the measurement to estimate the output. So output feedback event control may be designed. While in treating, we will discuss this problem in our forthcoming work. Moreover, the results studied here can also be extended to more complex nonlinear fractional DPS, and various open questions are still under consideration. Okay, thanks for your attention.